Okay, first reaction then, it wants us to look at the decomposition of phosphorus 5 chloride, which is solid, into phosphorus 3 chloride, which is a liquid, plus chlorine gas. So an enthalpy profile diagram, remember, looks like this, where you have enthalpy going up in that direction, and it tells us for this that delta H is plus 126 kilojoules per mole, and it's that positive sign that is the key thing here. That positive sign, remember, means that it's an endothermic reaction, so it takes in heat. And on this diagram, positive is up the page like that, and what it means is that it's taking in energy from the surroundings, taking in heat from the surroundings, if you like, and that means that the energy of the actual atoms and molecules themselves is greater, because if they're taking them in from the surroundings, the total energy doesn't change, and so there must be more of it locked into the system. So the endothermic change represents an increase in the enthalpy of the system going up like that. And when you draw it on the diagram, it's important that you label the states fully. So this is our starting state, and you must label it including the state symbol if you know those, because obviously if we had liquid PCl5 or gaseous PCl5, the energy level would be different, and so this wouldn't have the same position on this scale, and that's why the state symbols actually have to be there, because they are relevant to what this energy gap would be. So it's going to be a positive change, so we're going up the page, and so this is PCl3, which is a liquid, plus Cl2 gas. So those are the energy levels, and then what we mark on it is the enthalpy change. And when you do this, you should make sure that your arrow actually spans the gap. Don't just do a sort of quick arrow like that, because they won't necessarily interpret that as meaning that it spans the whole gap. So you have to draw that arrow fairly carefully and label it as delta H for the reaction. Or if it gives you a number, what's generally better and easier is just to write the number there as plus 126 kilojoules per mole. Okay, B, so we have the reaction of magnesium and dilute hydrochloric acid. So hopefully you remember this equation from the acids and bases stuff that we've done earlier. Metal plus acid gives you the salt, which will be magnesium chloride, and that will be aqueous because it's aqueous acid, so the salt will just dissolve in that acid, plus hydrogen. Okay, so if you didn't know that equation, you need to look back at the acids and bases stuff that we did earlier, where we talked about reactions like that. And it tells us for this one, delta H is minus 470 kilojoules per mole. And that negative sign, again, it's the sign, has this crucial information buried in it, which is that this is an exothermic reaction. So the atoms and molecules themselves are going down to a lower energy level, and therefore the sign of delta H is negative. But that means, of course, the energy's got to go somewhere, so it goes out in the surroundings, so energy is given out. So on our diagram, again, we put H up there, so we can put magnesium plus 2HCl there, and because delta H is negative, we're going to end up down here, so we get our aqueous magnesium chloride plus H2 gas at a lower enthalpy level, and the gap again, arrow spanning the whole gap, is minus 470 kilojoules per mole. Make sure that you put the arrow heads on there And make sure it's a one-way arrow, because it's got to show you the direction of the reaction, because it's only minus 470 if you're going that way, so that arrowhead is important. Question 2 wants to know first of all about the enthalpy change of reaction, which is written like this: delta, that's a Greek capital delta, little r, h. And what that means is that it's the enthalpy change when the number of moles shown in the equation react. Okay, so that's what you need to write down if you're asked what it means. So just to clarify a couple of things there. This word enthalpy, as far as we're concerned at A level, it means essentially the same as energy. It has a more precise meaning, which isn't quite the same as energy. Energy's a vaguer term, really. So it does have a very precise meaning, but you can just think of it as meaning energy in the way you think about it. So when the enthalpy changes, it means energy is taken in or out, and so on. And the point about the number of moles shown in the equation, obviously, is that every time a bond breaks, energy is taken in. Every time a bond is formed, energy is given out. And the more of those kind of reactions occur, the more energy is going to be given out or taken in. So delta H depends on the amount of stuff that's actually reacting. So we do the usual thing, we work in terms of moles. So if we look at the example of this reaction, which we had in question 1, delta RH for that reaction, the enthalpy change of reaction, would be the enthalpy change when 1 mole of magnesium reacts with 2 moles of HCl. Okay, and then it wants to know under what conditions can this be called the standard enthalpy change. So standard enthalpy change is written the same way, except that you add this little London transport sign up there afterwards, and what that means is that it occurs under standard conditions. The reason for doing that is that delta H changes a bit depending on the temperature, depending on the pressure, depending on the concentration if it's a reaction in solution. So you have to define the conditions under which it's measured. At a more advanced level, you learn how to correct for differences in those conditions. But as far as we're concerned at the moment, it's just about being aware that you have to define the conditions where it's measured. And the standard conditions are in terms of pressure, 1 atmosphere pressure. You can just write 1 atmosphere. You don't have to turn that into SI units. And for temperature, it's 25 degrees C unless otherwise stated. So for most A-level questions, 25 degrees C is what standard conditions mean. If it doesn't say anything, that's certainly what it means. But some groups of chemists use a different standard temperature. So biochemists, for example, will often use 37 degrees because it's body temperature. But as far as we're concerned, 1 atmosphere, 25 degrees C, that's what the standard conditions are. Okay, so in C we're focusing on this reaction of sodium and water, and it tells us that the enthalpy change of reaction is minus 362 kilojoules per mole. So first it wants to know simply, is it exothermic or endothermic? So it's the usual thing, you just look at the sign. The negative sign tells you it's exothermic, so heat is going to be given out. Okay, so that's the first one. And then it wants to know the amount of heat, the enthalpy change when 1 mole of sodium reacts. So the point here is that in the equation you've got 2 moles of sodium reacting, and remember the enthalpy change of reaction is the enthalpy change when the numbers of moles shown in the equation react. So 2 moles of sodium will give you minus 362 kilojoules, and therefore 1 mole of sodium is only half as much, so you'll only get half as much energy, which is minus 181 kilojoules. Okay, so that's the point. If only 1 mole of sodium reacts, you'll get 181 kilojoules of heat given out. In part 3, it wants the enthalpy change when 1 gram of sodium reacts. So as always in chemistry, when you see mass, you think, oh, that probably needs to be turned into moles to do anything useful, and clearly that's the case here because we only know the enthalpy change in relation to moles. So the first job is to find the moles of sodium, which is mass over Mr in general, but mass over Ar because it's just a metallic element, which is 1 over 23.0, which comes to 0.04348 moles. And we know that 1 mole gives you minus 181 kilojoules. So if you've got that number of moles, you've just got to multiply minus 181 by however many moles you've got. In other words, minus 181 times that number. So delta H is equal to minus 181 for each mole, times the number of moles you've got, times 0.04348, which gives you minus 7.87 kilojoules. Part D asks us to look at this reaction. Notice that in the question the equation wasn't balanced, so there should have been a number there for the number of oxygens, and it's easy to work out what that is because you've got 4 lots of 2 makes 8, plus 5 makes 13 oxygens altogether, so there've got to be 13 oxygens on the left, which is 6.5 times O2. So that would then be the correct equation for that, and it asks us if that's the delta H of reaction as written, what's the delta H of combustion? So if you consult your notes, delta H of combustion, which is written like that, is the enthalpy change when 1 mole of a substance burns completely in oxygen. Okay, so that's the definition of the enthalpy change of combustion. And you know, of course, that what you mean by burns completely is that when it burns, it gets fully oxidized, so all of the carbons end up as CO2 rather than carbon monoxide or carbon. So what you have to do is compare that definition with this equation, and you can see that's exactly what it is, because that is 1 mole burning, producing CO2, so it's undergoing complete combustion. So the answer is simply minus 5755 for the delta H of combustion. So you're going to have to get used to these different types of enthalpy changes, so reaction, combustion, also formation, which we'll get onto, but don't worry, we'll do lots of examples with those in later on, so if you're struggling to memorize them all at the moment, that should become easier as you get more practice with them. Question 3 focuses on this reaction, which you might recognize as the Haber process. It's a hugely important industrial process, and it gives us delta H of reaction, so that, remember, is the delta H when 1 mole of nitrogen reacts with 3 moles of hydrogen to produce 2 moles of ammonia. And then it's asking us what's the enthalpy change of formation of ammonia. So that's the definition of enthalpy change of formation, the enthalpy change when 1 mole of a compound is formed from its elements in their normal standard states. So that's not quite the same as this, because this is a reaction in which 2 moles of ammonia are formed. So if only 1 mole of ammonia is formed, the enthalpy change will only be half as big. So that's going to equal minus 92 over 2, because we're only making 1 mole, not 2 moles, to fit this definition, which is minus 46 kilojoules per mole. 3b is a neutralization reaction. Okay, so alkali plus acid goes to salt plus water, and it gives us again the enthalpy change of reaction, which is when 2 moles of KOH reacts with 1 mole of sulfuric acid. Now enthalpy change of neutralization, which we could I guess write like this, is equal to the enthalpy change when 1 mole of water is formed. So it's a very particular way of defining it, when 1 mole of water is formed in a neutralization reaction. And the reason it's defined like that is because that allows you to compare like with like, because remember, in terms of ionic equations, all of these acid plus alkali reactions, what's really happening is H plus OH minus goes to water. So what's really happening in neutralization is that the enthalpy change results from the H plus ion sticking to the OH minus ion to form water, and that's going to be expected to be the same for each mole of H plus, but obviously a mole of sulfuric acid contains 2 moles of H plus, whereas a mole of hydrochloric acid only contains 1. So you couldn't really meaningfully compare the delta H of neutralization of sulfuric and hydrochloric per mole of acid. But if you do it per mole of water formed, that's effectively the same as doing it per mole of H plus reacting, and therefore you're comparing like with like. That's the sort of background to it. But in the end, you just have to learn that definition. So in this context, the point is that 2 moles of water are formed in that reaction. So when 2 moles are formed, you get minus 116 kilojoules per mole. So in this case, the delta H when 1 mole of water is formed is minus 116 divided by 2, because we only want half as much water to be formed, so half as much acid and alkali to react, which is minus 58 kilojoules per mole.